Welcome to AI Paper Podcasts, your shortcut to the cutting edge of AI research.
Great to be here.
Today, we're diving into something, well, pretty fundamental for large language models. This challenge of optimal thinking. You see, LLMs, they're incredible, right? But they often get stuck in this weird paradox.
Yeah, it's a real balancing act.
On one hand, they can seriously overthink simple tasks, burning through compute, driving up costs, and you wait ages. Sometimes they even get the answer wrong after all that thinking.
It's like asking for the time and getting a lecture on the history of clocks, right?
Exactly. And then the flip side, they can underthink the really complex reasoning problems. They fall short just when you need that deep step-by-step analysis.
It's this core inefficiency, and it impacts, well, everything: latency, accuracy, cost, which is why this new paper is so important. It's OptimalThinkingBench, evaluating over and underthinking in LLMs.
Yes. This is by Pranjal Agrawal and the team at Fair Air, Meta, and Carnegie Mellon, just out August 19th, 2025.
Precisely. And they're proposing a really groundbreaking way to tackle this exact dilemma.
A new benchmark.
A new unified benchmark, designed specifically to evaluate this balance, to push the field towards models that are optimally thinking.
Okay, so what's the big reveal? The headline finding.
Well, and this is pretty striking right up front.
Yeah.
Currently, no single LLM actually is optimal. Not one.
Really? None?
Nope. Even the best ones, the state-of-the-art models, they still struggle to perfectly balance that efficiency and performance.
Wow. Okay, so today we're going to unpack that, this whole trade-off, what it means for how you use LLMs, and importantly, what researchers are actually doing to build smarter, more efficient AI.
Exactly. AI that knows when to hit the gas and when to hit the brakes.
Because let's be honest, if you're using LLMs regularly, you've probably felt this tension yourself.
Oh, for sure.
You're often forced to pick between different versions, right? Like a fast, non-thinking one versus a slower thinking one. Think GPT-4o versus o3.
Right, and you're making this tough call. Do I want speed and low cost, or do I need accuracy, even if it takes longer?
It's not ideal, especially for, non-experts just trying to get stuff done.
Exactly, and the paper makes this point really clearly. The goal isn't just a faster model or even just a smarter model. It's about getting to a unified model.
One model that does both.
Yeah, one that can adaptively decide all by itself, okay, this needs deep thought, or nope, this just needs a quick, direct answer.
Like an LLM with good intuition about problem difficulty.
Kind of like that, yeah. Knowing when to be Sherlock Holmes and when to just, glance at its watch.
Okay, so if this balances the goal, how on earth do you measure something like optimal thinking? It sounds fuzzy.
Well, that's the core innovation here, OptimalThinkingBench.
Right. Tell us about it.
So it's cleverly designed with two complementary sub-benchmarks. They work together. First up is OverthinkingBench.
Okay, judging by the name, this catches models thinking too much.
Precisely. Its whole job is to quantify excessive computation, wasted thinking on simple queries.
And what kind of simple queries were we talking about?
They put together about 1,440 high-quality questions, really diverse 72 domains, covering science, general knowledge, even everyday stuff like mechanics or global facts, alongside quantum physics.
Wow, that's broad.
And it includes different answer types, too.
Yeah.
Numeric, multiple choice, short answers, open-ended. Covers all the bases.
So how did they make sure these questions were actually simple and reliable for testing? Did they write them all by hand?
No, and this is clever. They use a synthetic generation pipeline. An LLM, Llama 4 Maverick in this case, generated the questions under constraints.
Okay.
Then, crucially, they use another LLM process, like an LLM as a judge, to filter them rigorously, checking for clarity, correctness, and making sure they were genuinely simple enough. It removes human bias.
Got it. So synthetic generation and LM judging. And how do they score it? What are the metrics?
They introduced a new metric called Overthinking Adjusted Accuracy, or OA8. Basically, did the model get the right answer within a set thinking budget, like using fewer than T tokens?
Ah, so accuracy penalized by length.
Kind of. And then they aggregate this into OA area under the OA curve. This penalizes any excessive thinking, even if the final answer was right.
Okay, makes sense.
Think of it like grading a student. If they write a brilliant 20-page essay for a simple yes-no question, yeah, they got it right, but they wasted a ton of effort. OA captures that waste.
Right, that clicks. So that's for stopping the models rambling on simple stuff. Yeah. What about the other end, when they don't think enough on hard problems?
Exactly. That's the job of the second part, Underthinking-Bench.
Okay.
This one quantifies insufficient reasoning, when models fail in complex tasks that really need proper multi-step thought.
What kind of complex tasks?
They've got about 550 questions across 11 challenging reasoning task types. Things like games, maze navigation, night swap puzzles, Puzzle 24, but also algorithmic tasks, graph problems like quantum locks, and tricky arithmetic like decimal count.
Okay, these sound genuinely hard. What was the logic for picking these specific tasks?
The core principle was selecting tasks where even a small model that's explicitly designed for thinking should significantly beat a large model that's not thinking step by step.
Ah, so tasks that inherently demand structured thought.
Precisely. They source them from Reasoning Gym using specific criteria like where a small thinking model outperformed a large non-thinking one by a decent margin like 10% or 30% accuracy.
Clever. And contamination, models seeing the questions before.
They avoided that by using procedurally generated questions, so no memorization possible. And the metric here is simpler, just standard accuracy. But it's often verified programmatically.
How so?
Like for the maze problems, they actually run code to check if the path the LLM found is truly the shortest one. Objective verification.
Okay, so you've got IUKAA hitting overthinking and standard accuracy on tough tasks hitting underthinking. How do they merge these into one single score?
They combine them using a standard F1 score, calling it Foot V1. It's the harmonic mean of IUKOA and the UnderthinkingBench accuracy, a cut.
And why the F1 score specifically?
Because it forces models to be good at both. You can't ace the optimal thinking bench just by being super efficient but dumb on hard tasks, or by being brilliant but incredibly slow on easy ones. You have to balance both aspects. It really pushes for that optimal sweet spot.
Makes total sense. A true measure of optimal thinking. Okay, the benchmarks sound really well designed, so let's get to the results. They tested, 33 different models?
Yep, a huge range. Open source models like Mistral, Llama, Qwen, GPT-OSS, proprietary ones like O3 and Claude, a real cross-section of the current landscape.
And what did they find? You already hinted that no one's perfect.
Yeah, that's the headline. No single model nails it. Only 5 out of the 33 even scored above 50% on the overall Optimal Thinking Bench F1 score.
Only 5? Wow, who came out on top?
O3 achieved the highest score at 72.7%. The best open weight model was GPT-OSS 120B, hitting 62.5%.
So a solid 10-point gap there between the best proprietary and the best open weight.
A noticeable gap, yeah. It confirms that optimizing this balance is still a major challenge across the board.
And digging deeper, what about the specifics? How bad was the overthinking?
It was pretty severe. Most of the models designed for thinking generated hundreds of tokens for simple overthinking bench queries.
Hundreds.
Yeah, many went over 700 tokens. Even when the extra thinking didn't actually improve their answer, even the best open models were still generating around 110 to 135 tokens on average for these simple tasks.
That's just computationally wasteful and expensive and slow for users.
Totally. It tanks their IUTAA scores.
Yeah.
Just a lot of unnecessary cycles being burned.
Can you give us a concrete example of this where a model just ties itself in knots?
Absolutely. The paper has some great ones. Take example 1, asking about UV protection. What layer protects Earth from UV radiation?
Okay, simple enough. Ozone layer.
Right. The model internally generated ozone layer pretty early on. Then it just kept going.
Oh no.
Started rambling, got confused between different atmospheric layers, terminology, and after hundreds of extra tokens, it spat out stratosphere. Wrong.
It literally thought itself into an error it initially avoided.
Exactly.
Yeah.
And another one, example 2, asking who sang thank you next?
Ariana Grande.
The model knew that. It recalled Ariana Grande.
Yeah.
But then, during all this excessive deliberation, somehow it brought up Lady Gaga, got confused, and ended up answering incorrectly. It argued itself out of the right answer.
Last slightly. Okay, so it's like that friend who overanalyzes everything and ends up more confused. That's clearly a problem. What about the underthinking side? How did the non-thinking models fare on complex tasks?
They consistently struggled compared to even much smaller models that were allowed to think step by step.
How badly?
Well, for instance, some of the Qwen 3 models, in their non-thinking mode, scored at or below 20% accuracy on UnderthinkingBench. But here's the thing. When those exact same models were run in thinking mode, their performance shot up. Qwen 314B, for example, saw a 34% accuracy jump just by enabling thinking.
Wow, that really highlights how crucial that systematic process is for certain problems.
Definitely. It shows thinking isn't just fluff, it's essential for complex reasoning.
Do you have an example of underthinking in action?
Sure. Example 4 involved path finding in a maze. The non-thinking model said, okay, I'll use breadth-first search, which is a good systematic approach.
Right, that should work.
But then it didn't actually do BFS. It just sort of traced a simple-looking path, probably the most obvious one, didn't check alternatives, and declared victory. Incorrectly, of course.
So it skipped the actual reasoning part. Classic underthinking.
Totally. In example 5, an arithmetic problem with hexadecimal numbers. The model made basic conversion errors right at the start, messed up intermediate steps because it wasn't verifying its work, and naturally the final answer was way off.
Just not double-checking its own reasoning.
Okay.
And earlier you mentioned distillation having weird effects.
Yes, this is a really interesting point for anyone training models. When they took non-thinking models and tried to make them better at reasoning by distilling them.
Meaning training them on the thought processes of bigger thinking models.
Exactly. Training them on those chain of thought traces. Counterintuitively, this sometimes made the distilled models worse on the simple overthinking bench tasks.
Huh. How?
For example, R1 Distill Quinn 7b actually had lower accuracy on simple queries than the original Quinn 2.57b it was based on.
So teaching it to think complexly somehow made it stumble on simplicity.
It seems that way. Pushing for complex reasoning capability via distillation might inadvertently degrade performance on basic recall or simple instructions. It's another tricky trade-off developers need to watch out for.
Man, this really paints a picture of models struggling to find that optimal gear. So given this state of affairs, what did the researchers try in terms of improving this balance? What actually helps models think more optimally?
They looked at a few promising directions. First, various efficient reasoning methods. Things like length-based reward shaping during training, model merging techniques, auxiliary task training.
Right.
Ways to encourage conciseness.
And did those work? Did they reduce the overthinking?
They did. These methods showed real promise in cutting down token usage up to a 68% reduction on OverthinkingBench. That's a significant saving in compute and latency.
Okay, that sounds great. But I sense a but coming.
Jekyll's, you said correctly. The big caveat was that these efficiency gains often came at a cost. Lower accuracy on the complex underthinking bench tasks.
The trade-off strikes again.
Yeah, 4 out of the 6 model method combinations they tested showed this drop in reasoning accuracy. It seems the benefits, especially those derived from math-focused training, don't easily generalize to broader reasoning tasks yet. Efficiency gains hurt complex thought.
Okay, so that's one approach with mixed results. What else? What about guiding the model based on the question itself?
Right, they explored question difficulty-based routing. The idea is simple. Use a router model up front to classify if a query looks simple or complex.
And then send it to the right mode. Fast mode for simple, thinking mode for complex.
Exactly. And this did help. It improved the overall OptimalThinkingBench F1 scores by between 2% and 11% compared to just using the best single mode. So the concept has merit.
But it's not a silver bullet.
Not yet. It was still significantly worse than a theoretical Oracle router, one that always picks the perfect mode. There was about a 12-point gap in the F1 score.
Why is it so hard for the router?
It's tough for one AI to perfectly judge the inherent difficulty of any possible question and predict how another specific AI model will handle it. It's a complex meta-reasoning task, and it remains a big, open challenge.
Makes sense. Okay, last approach. What about just prompting? Telling the model what to do. This is what we do all the time.
And this yielded some of the most actionable and maybe surprising results for everyday users.
Oh, tell me more.
When they explicitly prompted models with "don't overthink," just adding that simple instruction, it consistently led to a significant drop in the number of thinking tokens used on OverthinkingBench, up to 29% reduction.
Wow. And did it hurt accuracy?
That's the best part. It didn't impact accuracy on those simple tasks. And overall, it generally boosted the OptimalThinkingBench F1 score by up to nearly 9 points in some cases.
That's huge. Just telling it not to overthink actually works.
It seems so. It's a simple, direct instruction that helps curb that unnecessary verbosity without sacrificing correctness on simple stuff.
Okay, that's a massive practical takeaway. Now, what about the prompt everyone uses for hard problems? Let's think step by step.
Ah, yes. The classic chain of thought prompt. Here's where it gets counterintuitive.
How so?
For simple queries on OverthinkingBench, adding "let's think step by step" actually made things worse.
Worse?
Yeah, it increased the thinking length by 19 to 27%, and sometimes it even led to a small drop in accuracy. It basically triggered the overthinking problem on tasks that didn't need it.
So using that prompt for simple questions is actively counterproductive.
Pretty much. It makes the model more verbose and potentially less accurate. Now, for the complex underthinkingBench tasks, it can help slightly boosting accuracy by up to 2.5%.
Okay, so the takeaway is use "let's think step by step" only when you know the problem is genuinely complex and needs that structured thought. For simple things, maybe try don't overthink instead.
Exactly. Prompting matters, but you need to use the right prompt for the right job.
Fascinating. Okay, beyond testing solutions, did the paper dig into why models exhibit these thinking patterns? Any underlying reasons?
Yes, they did some really interesting deeper analysis, for instance, looking at question domain.
Like science versus history.
Right. They found models tend to generate way more thinking tokens for STEM domains, science engineering, compared to humanities fields like history.
Okay, maybe STEM questions are just harder.
You'd think, but here's the twist.
Huh?
This happened even when the accuracy was similar across the domains.
So they think more about STEM just because it's STEM.
It suggests a lack of flexible adaptation. The models might have this ingrained bias, maybe from heavy training on complex STEM examples, to just think harder whenever they see a STEM-related query, regardless of the actual question's simplicity. A learned reflex, almost.
Wow. Okay, what else?
They also looked at answer type. Numeric answers triggered substantially more thinking tokens compared to multiple choice or open-ended answers.
Again, maybe numeric questions are just harder. Calculations and stuff.
But again, this extra thinking happened without a statistically significant improvement in accuracy for most models on those numeric tasks.
So just seeing numbers makes them overthink.
It hints at mathematical tokens in the prompt might just automatically trigger excessive thinking, perhaps because complex math problems were a big part of their training. They assume math means hard work, even for simple sums.
Another learned reflex, overriding efficiency. What about dealing with noise or irrelevant info, like in multiple choice questions?
Yeah, they tested adding irrelevant distractor options to MCQs. It caused a near linear increase in thinking tokens. For every extra distractor option they added, the models generated, on average, 42 more thinking tokens.
Even if the option was totally nonsensical.
Seems so. It shows models get bogged down and overthink just because there's more stuff in the input, even if it's irrelevant noise. They aren't great at filtering it out efficiently during reasoning.
Incredible. Lots of wasted effort just processing noise. And finally, did the size of the model matter? Do bigger models think more efficiently?
Interestingly, not necessarily optimally. Looking across the Qwen 3 family, from smaller to larger models,
Yeah.
thinking token usage generally increased with model size on the OverthinkingBench tasks.
But did accuracy also increase proportionally?
Not really. Accuracy on those simple tasks stayed relatively flat for models 8 billion parameters and larger.
So bigger models were just more verbose, thinking more without getting better answers on simple stuff.
Essentially, yes. Larger models exhibited this unnecessary verbosity, this tendency to think more just because they can, without a corresponding payoff in performance for simpler problems.
Okay, so wrapping this all up, this deep dive into OptimalThinkingBench.
Yeah.
What's the big picture takeaway for us?
I think it clearly demonstrates that while LLMs are incredibly powerful, achieving this optimal balance, knowing when to think deeply and when to be quick and concise, is still a major hurdle. It's the next frontier, really.
And this benchmark gives us a way to measure progress.
Exactly. The paper's huge contribution is providing this unified benchmark, OptimalThinkingBench, and these concrete metrics like ACHIO AA and the F1 score. It gives researchers a clear target and a way to track progress towards building LLMs that aren't just knowledgeable, but also computationally wise.
Models that think optimally, not just maximally.
Precisely. Building models that are efficient and effective in how they apply their intelligence.
So here's a final thought for you, our listener. As these LLMs get woven deeper into everything we do, from writing code to analyzing complex data, imagine the impact of truly optimally thinking models. How might that fundamentally change not just how AI is developed, but maybe even our own cognitive workflows? Could it make human-AI collaboration faster, more seamless, maybe surprisingly more efficient than we expect?
Definitely something to ponder.
Thank you for joining us on this AI paper podcast. We highly recommend checking out the original paper by Agrawal et al. Lots more detail in there. We'll see you next time.